In the last section that we cover in Chapter 6, we're covering something called related rates. This is actually going to be very similar to implicit differentiation. It's kind of an extension of implicit differentiation. It's just now we're going to be looking at time specifically as our independent variable. So everything that we do in this section, we're going to be taking the derivative with respect to time. So what does that mean? So that actually means that whether we're taking the derivative of x or y, we treat it as implicit differentiation. And so if we look at the first one, what's the derivative of x? The derivative of x now becomes dx dt, which means that anytime we take a derivative of x, we have to multiply by dx dt. And other than that, the first part is the regular derivative. And then when we take the derivative of the other variable, like a y, this would be, if it's just y, it would be dy dt. Or if you take the derivative of something, more complicated, like a y squared, we would use our regular derivative rules, but then multiply by dy dt. So taking the derivative here should be very similar to what you were doing in section 6.4. But now we actually have to do that process for both x and y. Here's actually an excerpt from the textbook. It says, "It is common for variables to be functions of time. For example, sales of an item may depend on the season of the year. A population of animals may be increasing at a certain rate several months after being introduced to an area. Time is often present implicitly in a mathematical model, meaning that derivatives with respect to time must be found by the method of implicit differentiation." The idea is that you may not see a t in there to represent time, but it could be affecting the variables kind of behind the scenes, is the idea of this. And let's say you have two equations. You have an x equation and a y equation. Here it's saying that both of them in some ways are dependent upon time. And that's why we can take the derivative with respect to t. So if we look at this example that I have written here, it says, how fast is cost per month changing when production is changing at a rate of 12 units per month? So we've looked at cost functions before. We might let cost equal c, and production, we could call that x. And basically what this is saying is that both of them are based upon time, because we're looking at how fast is cost per month changing. We're looking at how production is changing. So the changing part is really indicating that we're looking at a derivative, because the derivative is really all about how something is changing. And so we'll look at this example in depth later, but just as kind of a heads up, if you have cost, if you take the derivative with respect to time, that's going to be dc dt. And that could actually be how the cost per month is changing. And if you look at production as an x variable, you could take the derivative with respect to time, and that would give you dx dt, and this tells us how production changes kind of per month. And it's that the time that we're dealing with here is month, but that's sort of the behind the scenes variable that we're working with in this problem. Okay, let's just look at a derivative example. So let's say x and y are both functions of t, and we're going to try to take the derivative with respect to t for this equation. So this equation might look like something really similar that you had seen in section 6.4, but the difference here is the derivative that we're taking. Now we're taking it with respect to time, so we need to treat both x and y as implicit differentiation. So let's go ahead and do that. This first piece I should mention this would be an example of where you need to use the product rule, and you could split it up as 2x as being a function and then y as being its own function. Maybe you could call one u and one v, and then that's what you would apply the product rule to. So if we take the derivative here, and let's do the product rule part first, I'm going to leave the 2x alone. Now I want to take the derivative of y, which it's going to be, instead of dy dx, it's going to be dy dt. Plus, now I'm still using the product rule here, so now is when I'm going to leave the y alone, but I want to multiply by the derivative of 2x, and that's going to be 2 times, again because the x variable does not match the t variable, we're going to multiply that by dx dt, the same process that we were doing in the implicit differentiation section. So I'm going to keep going. Now I want to take the derivative of 5x, so that derivative is 5. But x doesn't completely go away now because the variables did not match, so I'm going to multiply it by dx dt. Plus, now we're going to look at the derivative of 3y cubed, which is 9y squared. But again, that variable y doesn't match a t, so we multiply it by dy dt, and then equals the derivative of negative 51. It does not matter that it's taking the derivative with respect to time. The derivative of a constant is always 0. So now we've taken the derivative, and we can go ahead and simplify. There's really not too much that I'm going to simplify here, except maybe just getting rid of some of the parentheses. So if we were doing implicit differentiation, at this point is where we would try to get dy dx by itself, and that's not really possible here because we've got two different derivatives going on here. We've got a dy dt, and we've got a dx dt. So for these problems, you won't be asked to get one of those by itself. But you might be given some values to plug in. So for the second part of this problem, we're trying to find dy dt given these values for x, y, and dx dt. So instead of having you isolate one, what I want you to do is actually plug in all the information that you do know to find the last part that you're looking for. So let me go ahead and start plugging everything in here. 2 times x, we're given as x is 3. Times dy dt, this is the thing we're looking for, so I'm just going to leave that as dy dt, plus 2, y is negative 2, times dx dt, which we are given. Dx dt is equal to negative 6, minus 5, dx dt again, it's negative 6, plus 9y squared, times dy dt, which again I'm going to leave that alone because that's what I'm looking for. So at this point, because we are asked to find specifically dy dt, we will isolate that, but it's easier when we can go ahead and actually plug in all the numbers first and simplify before we even try to do anything like that. So let me just simplify a little bit here. And then I'm going to go ahead and keep simplifying here. We've got some like terms. So the 30 and the 24 we could combine together, as well as the 6 dy dt and the 36 dy dt. And at this point we're really close to having to solving for dy dt. we can just go ahead and subtract both sides by 54 and then divide by 42. So we get negative 54 divided by 42, and we can simplify that a little bit. Let's see, because both are divisible by 6. So the final answer is that dy dt is equal to negative 9 over 7. Let's look at an application problem. And this is actually referring back to the one that we had looked at in the very beginning, but now we're actually given an equation and values. So it says the total cost to produce X units per month is given by C of X is equal to 0.3x squared plus 7,000. How fast is the cost per month changing when production is changing at the rate of 17 units per month and the production level is 60 units? So just like with any word problem, we want to just break this down into pieces. So first we've got our equation. And we've got C and X in there, so we want to label what each one is. So C is our total cost. And X is the production. And it does indicate some stuff here, because it says the total cost produce X units per month. So it is kind of giving an indication of time. And so if we keep reading, how fast is the cost per month changing? So that's another thing that we're looking for. Cost per month changing. So if we try to break down what that means, that's what we're looking for, the cost per month changing. So again, that changing is sort of cluing us into that we need the derivative. Because it says cost per month changing, that actually means that what we're looking for is dc over dt. So how is cost changing per month? So we need the derivative with respect to time. So the next thing we have is when the production is changing at the rate of 17 units per month. So this is actually telling us information about production, but not production, how it's changing. So that means, again, derivative. So since production was x, this is telling us that dx dt is equal to 17. So we're looking for the derivative, and this per month here is indicating time. And the last thing we have here is that the production level is 60 units. So now there's no indication about months or changing, so this is just the x value, the production. So that is going to be that x is equal to 60. So let me go ahead and write our equation again. C is equal to 0.3x squared plus 7,000. And what we're going to do is take the derivative with respect to time. So I'm going to write that as d over dt. So for the c, since it's all by itself, that's just going to become 1 times dc dt, but I'm just going to write the dc over dt. So the derivative of cost with respect to time is equal to, now let's take the derivative here. So I'm going to bring the 2 to the front, so that's going to become 0.6x. But here we took the derivative of x, doesn't match that variable time, so the extra step is to multiply by dx over dt, and then plus the derivative of 7,000 is 0. So we've got dc over dt is equal to 0.6x dx dt. And once we've taken the derivative, we can go back to see where to plug everything in. So we were looking for dc dt, so I'm not going to plug in anything here. This is what we're trying to find. Dx dt is 17, So this is where I'll plug in the 17. X is 60, so this is where I'll plug in the 60. So our answer is going to be 0.6 times 60 times 17. When you plug that into the calculator, you should get 612. So if we think about the units for this one, this would be 612. Total cost, we can just assume that's going to be dollars. $612 per month. Now let's look at one more application where we're not originally given the equation. So for this one it says a snowball is melting at a rate of 0.9 feet cubed per minute. Find the rate of change of the radius when the radius is 1.7 feet. So since we're dealing with a snowball here, we're dealing with a sphere, and we're dealing with the volume of it. The volume of a sphere is 4/3 pi r cubed. This is not a formula that you would need to memorize for the exam, but I just want to show you some examples where you can use the geometric formulas and then apply related rates. So this is our formula for volume. It says the snowball is melting at a rate of 0.9 feet cubed per minute. So it's this per minute that's telling us that we're dealing with this implicit variable time, and the rate is telling us that we're talking about a derivative. So I'm going to come back to that one, but I want to read the rest of this too. So find the rate of change of the radius. So this rate of change means derivative of our radius when the radius is 1.7 feet. So that just means that we have this melting snowball, but if we freeze it right when the radius is 1.7 feet, that's what we're looking at. Okay, so we have our clues here that are talking about a derivative with respect to time. So what I'm going to do first is take our volume equation and take the derivative with respect to time. So that ends up being, on the left, dv dt, so the derivative of volume with respect to time, is equal to, now remember that pi is just a number, so 4/3 pi is just a number, and so it's just acting as a coefficient of r cubed. So I'm just going to write 4/3 pi times, now we want to actually take the derivative here. So the derivative of r cubed is 3r squared, but because we're doing the derivative with respect to time, the extra thing to multiply in is going to be dr dt. And I guess I didn't label all the values like I had before, so I'm going to go ahead and kind of pause right now and do that. So we had the part in green there, it says that was the melting rate. That's actually going to be dv dt. And so the melting rate, it also, I can look at the units to help me out with that. So if it's cubed, it's telling me it's dealing with a volume. So if it's melting at that rate, that actually means it's going to be a negative 0.9 feet cubed. The negative is indicating a decrease. And we're looking for the rate of change of radius, so dr dt. We're not going to plug anything in for, that's what we're looking for. And then finally, we have that r is equal to the 1.7 feet. Okay, so now we could plug things in, and we might do a little simplifying before we plug it in. You might notice you end up with a 3 in the denominator and a 3 in the numerator, so I could rewrite this as dv over dt is equal to 4 pi r squared dr dt. And now I can go ahead and plug everything in. So we're looking for dr dt, so that's going to be left alone. We have a radius value, so I'm going to plug in 1.7 for the radius, and the melting rate, I'm going to plug that in for dv dt. So that's going to be negative 0.9 is equal to 4 pi times 1.7 squared times dr dt. So if I write that out, I've got that dr dt is equal to negative 0.9 divided by 4 pi times 1.7 squared. And now I'm going to go ahead and plug this into my calculator. And when you plug it in, you should get about negative 0.0247. So I'll round that to 5 for right now. So that means the radius is decreasing by a rate of, and notice that I haven't actually put the negative here because I used the word decreasing. So the radius is decreasing by a rate of 0.025 feet per minute. And that's our final answer for this one.